Problem 126, chapter 5. Here we have this part which has the circular slot on it. The whole part is moving with angular velocity of omega, capital omega, and angular acceleration of capital omega dot. And we have this particle which is moving on this slot. And at the moment, it is moving to the right with the constant speed of u, which is given. U is going to be a given number. And the question is, what is the actual velocity of this point, this ball, and also actual acceleration of it? Keep in mind, this u is the velocity with respect to this part, to this sector. Okay? So before I ask you to think about it, just imagine we have two coordinates here. This is small x and y coordinate. Let's say it is stick to this sector. So this coordinate x and y, it is rotating with this object. So it's going to rotate with angular velocity of omega and angular acceleration of omega dot. And also, let's say we have another vector, another coordinate, capital X and capital Y, which is fixed to the ground. So this small xy, it is rotating with this coordinate, with this sector. So try to solve this problem yourself. Pause this video, think about it for at least 10 minutes, then see the rest of the video. So I'm gonna guess you did that. Now, how we can solve this problem? So first of all, we need to find the velocity and acceleration of this point in the rotating coordinate, in this xy coordinate, which, if you remember, we call them v rail and a rail. Velocity relative to the moving coordinate and acceleration relative to moving coordinate. So what is v rail? If you sit on this sector and rotate with it, then if you look at this point, you're gonna see it is moving to the right with the velocity of u. So the relative velocity is gonna be u in the I direction. How about the acceleration of it? What is the acceleration of this particle on that frame with respect to this sector? So if you sit here and look at this point, you're gonna see this point is moving on the circle. So in general, it's gonna have two accelerations in your eyes. Acceleration in the tangential direction and acceleration in the normal direction, right? What is the acceleration in the tangential direction? It's gonna be u dot, right? But what is u dot? U is a fixed number. U is constant. So this ball doesn't have any acceleration in the tangential direction because u dot is equal to 0. How about the normal direction? It is not moving on a straight line, it is moving on a curve, right? So we have a particle which is moving with a constant speed on a curve. In that case, if you remember, it's gonna have normal acceleration. And the normal acceleration is towards center, and the magnitude of the acceleration is velocity squared divided by r, the radius of curvature of the path, right? So acceleration with respect to the sector or a rail is going to be u squared divided by r2 downward in the negative j direction. So it's going to be negative u squared divided by r2. Now, after finding v rail and a rail, now we can use the previous equations to find actual velocity and actual acceleration of this ball with respect to the big xy coordinate, with respect to ground. Velocity of A is equal to velocity of B, the origin of the coordinate, plus v rail, plus omega of the coordinate, which is capital omega in the k direction, cross r. R means the location of the points in the rotating frame. So BA, right? BA is my R. So it's going to be equal to velocity of B is 0, velocity, the V rail, we found it here, it is U in the I direction, plus omega, omega is positive in the K direction, so it's going to be capital omega K, cross product to BA, and BA is R2 in the negative J direction, so negative R2 J. K cross J is negative I, two negatives positive, so altogether it's going to be U plus R2 times omega all in the U direction, in the I direction, U plus R2 times capital omega all in the I direction. So this is going to be the actual velocity of the particle. How about the acceleration? Let's just start with the equation. Acceleration of A, the actual acceleration of the point is equal to acceleration of B plus relative acceleration plus alpha cross R plus omega cross omega cross R plus 2 times omega cross V rail. I wrote down the equation first. Now we can plug in all the values. Acceleration of A is going to be equal to acceleration of B is 0, it's a fixed point. The relative acceleration of the particle in the rotating frame, found it here. So it's going to be negative U squared times R2 in the J direction. I forgot J here. Plus alpha cross R. Alpha is the acceleration of the rotating frame, which means this omega dot. So plus capital omega dot, which is in the K direction. Cross product R, and R is this, right? Let me show it here. This is my R, which is R1 in the negative J direction. Negative. Plus omega cross R, again you can replace it with negative omega squared, so negative omega angular velocity of the frame, which is capital omega, times R, and R again is R1 in the negative J direction, plus 2 times omega, 2 times capital omega in the K direction, this is my omega, cross the relative velocity, and V rail, we found it here, right? It's U in the I direction. So we have only one cross product here, K cross I is J, so I'm gonna have 2U times capital omega in the J direction here. And if you add all of them together, we are gonna have acceleration of A is equal to R1 capital omega dot in the I direction, plus if you combine all the J terms, we are gonna have R1 times omega squared plus 2 times omega times U minus U squared divided by R2 in the J direction. And also the other part of the question is, what is the Coriolis acceleration? So as you remember, we said this part is the Coriolis acceleration. So this is the total acceleration, Coriolis acceleration of points A in this rotating frame is 2 times omega cross V rail, which is going to be this part, right? And also K cross I is J, so altogether it's going to be 2 times omega times U in the J direction. So this is going to be the Coriolis acceleration of point A in xy coordinate, small xy coordinate.